So, good morning, everyone. I'm Wei Jiaxu. I'm the research director for the Good System Smart Cities, and I'm also the group manager for Scalable Computing Intelligence Group at TAG. The Good System is a UT Grand Challenge project, and with a mission to developing human AI partnerships that benefit societies. The smart cities technology have the great potential to contribute to these missions. So to advance our knowledge and facilitate research discussion around smart cities, we start these lighting presentations on every Tuesday morning. Today, we are very happy to have the presentation from Dr. Zheng. Dr. Zheng is a professor from mechanical engineering in Texas A&M University at College Station. Dr. Zheng's research concerns energy efficient buildings and smart building controls with a focus on high efficiency HVAC systems. So we're delighted to hear the presentation on smart and connected buildings from Dr. Zheng today. So Dr. Zheng, if you're ready, just please go ahead to share your screens.
Can you see my screen now?
Yes.
Okay. First, thank you for the introduction. So I'm Dr. Zheng O'Neill from the Department of Mechanical Engineering in Texas A&M University. So today I'm going to talk about towards the smart and connected buildings in the cities through the intelligent building operations for efficient, resilient, and healthy buildings. So first, briefly talking about motivations. Then I will also talk about challenge. Since this is very short presentation, I will briefly cover example to talk about occupant central control in buildings, which mostly are only going to cover the National Energy Saving Potential Assessment for OCC. And then I will have a few slides talking about opportunities. So why we need to talking about building energy consumption, talking about smart buildings, energy efficient buildings, resilient and health buildings, because the building energy use matters. So this pie chart basically shows the US energy consumption by three sectors: industry, transportation, and the buildings. So you can see building actually consume 45% of the total US source energy. This is very similarly worldwide, 75% of electricity and 54% of natural gas in the US is consumed by the buildings as well. And then the ratios actually are not changed in time. If you see this plot, basically shows the those energy consumption ratio from three different sectors over the years, covered from 1960 to 2040. So you see actually from both residential and commercial buildings, I mean, by the 2040, the ratio is still going to be very similar. So as mentioned, for the building operations, they consume 75% of the US electricity. And then here I show very famous the dark curve. So in this dark curve, y-axis is a net node. That net node is the difference between the forecast loading, including the building load, and the expected electricity production from various generation resources. So these include the generation from wind turbine, from the solar PV, etc. And the y-axis, that's y-axis, x-axis, that's for the the whole day. So you can see if we can actually do something from building side, we can provide the better power grid resilience. So for instance, if we can kind of do some load shifting, and from this like late afternoon to the noon, and all we can do the load shedding, and then this actually going to provide a better solution for grid resilience and grid sustainability. So in general, node site management from buildings give us the great opportunity and challenge for building node shifting and node shedding. Then what's the reality for the energy efficiency in buildings? So this is actually the very famous diagram cited by many papers. This is from USGBC, Leadership in the Energy and Environment Design. So for those buildings, you can see before they construct those buildings, you have proposed savings from simulation. After building is occupied and then they have those measured savings. And then you see actually there's a big variations in terms of the comparison between the measured savings and actual proposed savings. So for those buildings, they are actually saving more than the expected. For those buildings, they're saving less than expected. And then for those buildings, they actually use more energy than the code compliant baseline. So why you have those the big variation? In here, I list the 5 the factors contribute to this the variability. I'm only going to cover this the last 3 because they are associated with the building operation. First one is uncertainty in operation environment nodes and the human building interaction. So these basically cause the inefficient operation, and also occupant behavior plays the very important roles for building energy consumption profile. Last one is related to the faults. So because you have all different kind of faults in the building operation, from sensors, from controls, from HVAC equipment, these also cause inefficient operation. And then there's some ongoing research effort related to intelligent building operation. This covers advancing sensing. So people are using the occupancy sensors to detect the people, and also use advanced temperature sensor, humidity sensor, etc. There are smart controls. Those smart controls came from optimal model-based control, like model predicted control, or model-free control. Like recently, lots of people talking about using machine learning-based method, reinforced learning-based method. And the third one is related to energy diagnostic technology. So you can treat the building as the patient, and then we are proposing them energy doctors roles, so you can diagnose the different faults from buildings. Last one is related to human building interactions and well-being in building environment. There are quite a bit of challenges right now for intelligent building operations. The first one is related to the data issues. So there's a significantly large amount of the data available from building automation system, and also those data are less vast. And then the models most of the time are too complicated, cannot be directly used in the building energy management system, and the control sequence sometimes work pretty well in the simulation environment. But if you want to implement in the real building, it's a challenge and also a cost. I will briefly talking about example. Basically, that example is for occupant central controls. We are using the simulation to do the nationwide energy savings potential assessment for OCC. So in this project, we have Energy Plus as our simulation engine. We have the 4 different building energy models, which covered on crawl space, slab, heated bases, unheated basement, and then we pick up the 40 American cities, so based on population, also based on the representative city for international energy code, international energy conservation code climate zones. So that's the 40 cities. We pick up the 40 study, and then for occupant schedule, we assume there's 2 people in the house, and then we come up with this schedule using the Building American occupant central control schedule, and then we did some sampling and k-means method to finally generate the occupancy schedule. These basically is 2 people, sometimes sort of people that in the home that during the night, and then they are out for work, right? And then there's the 5 different temperature set point control strategies. The first one is baseline, and then the last 4 is related to occupant central control. So if you look at this, the bottom one, this is the most energy efficient one, which you have 2 degree occupant setback, and also 8 degree occupant setback, and 1 hour smart recovery. So totally there are 16,000 residential simulations. And then this heat map basically shows the simulation result from that 16,000 simulation. Y-axis It's different cases using different energy code. I-axis, that's 40 cities. And the color of this heat map indicate HVAC savings ratio. The check mark means you have the case actually has more than 30% of the HVAC savings compared with baseline. The check mark means the case only has less than 15%. So the key takeaway from this study is a deep setback temperature could bring 5% and to 10% additional savings compared with the light setback strategy. Last one is if people can adopt an environmentally friendly temperature setback, that's going to have a big booster for building energy efficiency. So in next few slides, I will just briefly talking about some opportunity I see for this area. The first one is about smart ventilation control. So basically, this one, we're trying to propose some control strategy can switch over the normal modes and the pandemic modes, because right now in COVID-19 pandemic mode, most of the stay at home and even in office, the CDC and actually recommended to have 100% outdoor air. So the goal for this project, we're trying to see whether there's a minimal ventilation rate for different HVAC system in most common public buildings, including schools, office, and retail store to minimize infection risk. So another objective is trying to see whether there's a correlations between the CO2 and the virus. So we can use the CO2 concentration as an indicator to control the ventilation rate, because both CO2 and the virus are generated from occupant, but normally we don't measure the virus in the space, but we can easily measure CO2 concentration. So that's why we want to see whether you can use the CO2 as an indicator of the infection risk, and then for the use that to do our smart control for ventilation. So the next opportunity I want to talk about is the sensor-based optimal energy management through the human building interactions, IoT-based, NAF extended energy management. These include self-learning for the immune system. And then we're going to also talking about energy diagnostics and prognostics using the multiple data source. So instead of traditional temperature sensor, humidity sensor, here there's opportunity to look at acoustic sensor, thermal air image, low-cost particle sensor to help us to do some diagnostics and prognostics for smart building application. So for example, in my group right now, we're doing a DOE Building American project. That's the IoT-based comfort control and full diagnostic system for energy efficient homes, right? So that's the homes in here. Another opportunity is the grid inductive efficient buildings. As I mentioned, building actually consumes 75% of electricity in the US. So how we can do the load management from building side is going to be critical for power grid. So everyone actually in here in Texas experienced some issues in the February Texas storm, right? So that's really actually a balance between the load side and the supply side. So one way to do that is actually using some storage system. We can use the building as the virtual battery. So in this project, we are explore cost-effectively thermal active building system to support a power grid with a high penetration of available renewable energy resources. So basically, building is using a virtual bed through using the phase change material, enhance the thermal active structural panel. So that's the structure panel. And then through some optimization, you're trying to understand when is the best time to charge and discharge PCV, the phase change material. So last opportunity I want to talk about is the well-being in building environment. So well-being is being, right now is hot topic because everyone wants to do the people-centered and the human-centered control, right, for the smart buildings. Well-being is strongly dependent on the link between the building environment and the person, cultural and the social factors drive health, productive, and comfort. So you can see in here, basically at least a few environmental factors which are associated with the well-being in building environment. So through the better understanding of the well-being in building environment, we can inform better building design, construction, operation, and use. Right now, we have ongoing NISA project This is for international network of networks for well-being in building environment. My last slide, I want to briefly talk about the smart building test facility at Texas A&M. So we right now have the two identical side-by-side modular homes. So those two homes are going to be used to study connected homes. And then we also have the two test bed to study those HVAC equipment for grid interactive efficient buildings. One is for the control test bed, other one is for the water source heat pump test bed. Everyone is talking about electrification. So with more and more renewable energy, and then the key for residential buildings, to participate in this electrification is to use the heat pump. That's all I have for these 15 minutes. I'm open for questions.
Oh, thank you very much. It is a very compact 15 minutes. I've covered a lot of information. I want to see if there's any question from audience. So one thing I'm interested, like we have been in discussion internally, is I want to ask, like, do you see like maybe we have a major usage pattern shift in terms of the more people start to adopt the electric vehicles, and how that might be impact on people electricity usage? And on the other hand, is there's also a trend on people start to install solar on their own home. So how those new energy sources and the potential huge energy consuming product can impact existing studies?
Yeah, so that's when we're talking about a smart connected community, then we have to actually consider the homes, also commercial buildings, and also the things you just mentioned, those EV, electric vehicles. So because in the end, they are actually going to load for the power grid. So as mentioned, load side management is critical to reach a smart and connected community, to provide some key features to enable the power grid resilience. So that's the key to do the load side management. So load side management in here is not just like buildings. You have to actually talking about, as you mentioned, the EV charger. And then like in our smart home test facility, we have EV charging station. So that EV charge station is give us kind of the capability to study the behavior, right, for the load profile, a different load profile from the connected homes. So the homes is going to have the EV charge station. The home is also going to have the battery. The home is also going to have the PV for the power generation. Some homes, I know they have solar thermal system, to use the solar thermal system to generate hot water for domestic hot water usage in homes. Yeah. So all those things I think need to be connected together. Again, for connected community, no single component can be left. So you have to consider all those components in a holistic framework.
Okay. Thanks. So, but the other thing I'm wondering is like we can connecting all the sensors and all the usage together, but how? So, do you envision a more like a AI-based control to optimizing the usage on the production side, or the smart sensors there is more make the energy usage more informative and transparent to residents, so they can do adjustments?
So for those smart sensors, the smart meter is going to provide the data. Those like in our one of the projects, we're using the LT-based devices like a smart vent, and also those temperature sensors, humidity sensors, flow sensors, occupant sensors. Those sensors provide information for our we call it adaptive controller. So for that controller is going to take the information from measurement, and then there's some algorithm behind that adaptive controller. So, and then the controller is going to take the information from sensors and make the recommendations to the HVAC system to say when you're going to turn on, when you're going to turn off, what kind of the optimal thermostat set point should be. So sensors really, smart sensors, IoT devices, really actually a key, I should say, key labels for the smart homes. Without those the smart sensors, without those IoT devices, it's impossible to have the smart homes.
Right. So, so the sensor is really just gathering information, and but is there a work on trying to make optimized decision automatically, so the smart home can really be smart in react to environments and to the needs?
Yeah. So sensors sending information, you could actually send like right now you have Ecobee sensor. You also have those Google's the Nest sensors. So those sensors, they collecting information. They have some onboard algorithm to help make a decision, and those decision is going to send to the like a heat pump, your AC system, the home. So those decision, it depends on what you call. Sometimes it's rule based. Sometimes actually is machine learning based. You actually people basically you have to install those sensors for a couple of weeks and then learn your behavior. And then based on that behavior learning, and then you can, the thermostat, the smart thermostat is going to choose the set point for you. And then so you can make it more, make the system operate in a more autonomous way.
Yeah, I guess I'm more interested on the machine learning part because my background is in computer science side. So I was always wondering like what exactly those smart sensor can do. Like for example, the smart thermostat, it seems like it can learn your behavior, so it can automatically setting things to you. It is a way of convenience, but it doesn't necessarily means to optimize the energy usage. So that's sort of like where my question coming from there.
Yes, so you could actually, like in our those prototype sensors system, I should not call it sensor, it should be the sensor system. You take the information from the, you can take the information from those smart sensors, temperature sensor, and also the occupancy sensors, tell whether it's people in the space or not. And then you can actually come up with your own optimal solution through some machine learning methods, through some optimization algorithms. Since for the home system is not complicated, we'll be able actually to implement those optimal solution in a Raspberry Pi. And then you basically use that Raspberry Pi as a brand for your home operation. And then that Raspberry Pi is going to manage your AC system on or off. You can do that. Yeah.
Interesting. Yeah. Yeah, I just worry about like I had a bad habit to use a thermostat, and then my smart thermostat only will learn my bad habit in a way. Is there any other questions from the audience here?
Yeah, I actually have one question. Yeah, I'm just thinking about, you mentioned that the built environment can be a really good, the built environment should be related to the energy consuming. And so, you know, currently the carbon pricing is kind of hot topic. Do you think this kind of like carbon pricing can be one political solutions to like the high consuming energy?
Yeah, so right now, actually, like in ASHRAE, also DOE, Department of Energy, American Society of the Heating, Refrigeration, and Air Conditioner has a task group related to decarbonization. So basically, that's that building actually, you think about energy consumption, electricity consumption, 75% also contribute a lot to the carbon, right? So that's why if you can reduce the energy consumption from building sector, you can have the whole society to reach those carbon neutral faster. So that's why in the building community, whether people is working on individual building or working on the collected communities, they are on the same page, which is that you need to reduce energy consumption. Then that can help the society move towards to the carbon neutral. Yeah.
Thank you.
I have a question, Dr. Zheng. So in your opinion, what's the so we have many smart home devices and the sensor especially. So what's the biggest barrier opportunity for the commercialization opportunity for smart home devices, especially for sensor devices?
Cost.
Cost.
Yeah, there are most like we have a API project which will evaluate those different occupancy sensor to enable smart thermostat. So the key varies. One is the cost, other one is accuracy. But for accuracy, that one, I think right now with advanced technologies in the sensing, advanced sensing technology, and then accuracy could be improved, but cost really actually is a key barrier to have those to basically to integrate those the smart sensors into the smart home systems. Other one is since it's about interoperability. Basically, you have the sensors from different manufacturers. You may have CO2 sensor, you may have the temperature sensor, you may have the different IoT devices like the smart van. How they can all talk with each other, and then in the end, they're going to make the same decision, right? You need those the sensors talk with each other. They only need those sensors in the end talk with the central, we call it building management system and the hub, and then the hub is going to make the decision. So the interoperability also is the key barrier in current smart building community.
Is there any like iPhone or Android? Is there any common or Windows or Mac? Is there a common operating system or like communication platform or like when you mentioned there's different specification for different sensors. So is there any leading one who is everybody trying to build their sensor based on that platform?
Like for the smart homes, if you're using wireless, so people talking about Zigbee, you can use the Zigbee's protocol, and then that's the protocol, right? But in terms of like the apps, I have been seeing the apps in different platform. That really actually, I think is really depend on user, because user, you can prefer different platform. What we care more is on the communication, right? So how the sensors communicate, and then in the end, the dashboard, that is really not a big issue. So again, the communication protocol, right now, very popular one as mentioned is the Zigbee. That's a wireless communication protocol you can use in the smart homes. For the commercial buildings, it's more complicated. So for commercial buildings, the most popular one used in the commercial building is the BACnet. That's the kind of data communication protocol proposed by ASHRAE. So that's one. Most of the modern buildings, actually in the US, if the building is built in last 10 years, they will going to support this BACnet communication protocol.
Thank you.
So is there any more questions for Dr. Zheng? All right, I think it's right on time, on 10:30 now. So I want to thank Dr. Zheng again for this wonderful talk, and I have learned a lot. If you're interested in our talks, and we have another one next week, and you can follow us on our website on smartcity.tech.utexas.edu to follow us on the future events. So we will collecting the recording from these sessions and post it online as well. Thank you very much, everyone. Have a good day.